Hello and welcome to this masterclass on shading in Houdini 15. My name is Kai Stefkinski. I'm a Senior Technical Director at Side Effects Software. And in this video, I'll talk to you about shading in Houdini 15, both from an artist's point of view as well as from a more technical perspective, where we'll learn how to build your own shaders from the most fundamental components. And I'll start off by just looking at some of the materials that we ship now with Houdini 15. You can find these on the material palette, where you find that the collection has grown quite a bit. So we'll have some simple materials like this rubber shader here, which doesn't have any textures applied. It's supposed to give you a quick start at dialing in some of the BSDF values like the roughness and color. They're all balanced against each other. And then you can go and apply your own textures to get local variations, object-specific textures that you might need. Some of them are textured as well, so they come with high-quality textures that we shot specifically for these materials. And then things like these metal shaders. The values on these are actually based on real-world measurements. So things like the refractive index and extinction coefficient are set to the real world values here. You get very accurate results from these. And you'll find that most of these are based on the new principal shader. One big difference to older versions here with the gallery materials is the old versions used to be unlocked just VOP materials. So you could dive right in and make changes to these, which you can still do if you unlock these. But these are now based on digital assets that are actually caching their code. So if you dive inside, you just get this notice here, and you'll find that you don't have any nodes loaded inside. The advantage of that is when you have lots of shaders in your scene, the scenes are now much faster to load. And also starting up renders should be a lot faster because Mantra doesn't have to generate the Vex code from the VOP nodes contained inside. It just has this one node and already has the code ready to render. So let's have a look at the principal shader itself. This one here is just a pretty default principal shader where I just applied some displacement mapping so we get some more interesting reflections here. You'll notice that the interface of this is very clean and has a very reduced set of parameters. But with these parameters, you're still able to get quite a large variety of materials. All the parameters on this are in the 0 to 1 range, which sort of makes it much easier to texture these. And some things like the metallic parameter actually do quite a few things under the hood, where just setting this one parameter already gives you, a fairly accurate metallic look. And to get this with some of the older shaders like the Mantra surface, you actually had to know quite a few things about how metals behave, just to be able to set all the right parameters to get something like this. So the difference here is that we sort of do this for you under the hood. And for example, one big difference here between the non-metallic and metallic look is with the non-metallic. If I set a base color value here, an actual color, one big difference is the way that color affects the various components of the shader. You'll see that if I add some extra image planes here for the direct lighting. That the base color actually only affects the diffuse component here, which is the correct thing to do for non-conductive materials, which is what I'm rendering when I have this set to 0. And the reflection is actually uncolored. Now I can, just for additional artistic control, you also have this reflection tint where you can tint the reflection by the color. But by default, For physical materials, that's not really what should happen, because the reflections of dielectric materials don't depend so much on the wavelength of the light. So light is reflected fairly uniformly. So, the reflection color basically matches the light color here. And it's the same for code reflections, which I don't have here yet. And if I switch to fully metallic, you'll see that we don't actually have any diffuse anymore. And that's because conductive materials don't really have a diffuse component. The diffuse lighting is really the result of light being scattered inside the objects at short distances and exiting the surface again, and that doesn't happen with metals. So as you increase this metallic parameter, we fade out the diffuse here. And if we look at the reflection component, you can see that basically everything happens in here. And this is colored now. And this is because with conductive materials, the wavelength of the light changes the intensity of the reflection that you get from the surface depends a lot on the wavelength of the light coming in. So this is how you get this colored response. Now let's try to make some other materials out of this. You'll see that usually when I do that, I only have to touch like 2 or 3, maybe 4 different parameters. For example, if I wanted to go to something that looks more like a simple fabric shader, I just increase the roughness and add some of this sheen here, which is intended to simulate the look of little fibers on the fabric being illuminated from behind, where light is transmitted through there. Sometimes helps to increase this beyond 1. Turn off the displacement for this one. So you can see that you can very quickly get to this sort of soft fabric look, where, to get totally realistic results, you would still need some textures on here. But you can get to the basic BSDF settings very, very quickly. It's also very easy to make something like a coated metal shader, for example. Just turn this back on, turn off the sheen, reduce the roughness a bit. We'll go to a nice saturated red or orange, and then just add a coat reflection on here. So this gives you a sort of dielectric coat on top of this. Just have a look at the individual components. So again, we don't have a diffuse. We have the colored specular and the coat layer on top. Just add back the displacement here. So you can get quite a large variety of looks here. And of course, like I'm showing you here, we also have besides the surface shading itself, we have some other features here that you find on most of the generic shaders that we ship, like the Mantra surface as well. So we have different ways of applying displacement. We added out-of-the-box support for vector displacement in UV tangent space now. So you can bring over displacement maps like that from other packages. We have an emission component here where you can apply a texture as well, and various forms of bump mapping. One new feature here is you have separate control over your normals and bump mapping for the base and coat layer. So for example, turn this off. By default, coat is applied to, the bump map is applied to both the base and coat. Let me just see if I can make this obvious here. I'll just add some roughness to the coat layer so we get a larger highlight there. So you can see that the highlight is affected by the bump map there. I'll just turn off the preview. And if I switch to code and activate the separate code normals, this actually now defaults to a flat surface again. So the base layer underneath is affected by the bump map, but the top layer isn't. So now I can also do it the other way around, of course. So I just disable this, add a bump map on here. I'll just pick the UV grid again. So now you see that only the code layer is affected. I think I have a very, very high scale value on here. So any combination of these should just work. And this is on the Mantra surface shader as well. We also support UDIM textures out of the box now. So that's a switch here that enables this. So any of the textures you apply in here are gonna work with UDIMs out of the box. To do that, you just use this syntax in your shaders, in your texture names. So this is going to be replaced with the UDIM ID, just based on the UV coordinates. And ptex has been supported for a while, and it's just going to work as well. Let's have a quick look at the Mantra surface shader as well. So this is also an HDA now. So since this is quite a complex big shader, the code caching that I talked about before makes quite a big difference with this one. So just in our own files where we generate our gallery shaders, where we have like 30 different files now, the load time I think went from something quite noticeable to basically making no difference between loading an empty file and loading something with the 30 shaders. So this hasn't received any huge updates apart from the code caching, but it does have the separate bumps and normals, and the new methods of displacement mapping, so the vector displacement as well. So that's on this one as well, and of course UDIM textures. One thing we have done with this is just give it some more physically correct defaults. So it used to be that Fresnel blending wasn't on by default, and it just had some fairly random intensities set on the various components. So these all default to 1 now, and due to the Fresnel blending, they're blended correctly, and so by default you get a physically correct result. With this shader, it's still a bit harder to balance everything compared to the principled shader. Like you need to take care that you set all the right values for specific effects. But it can still be just a very powerful, very generic shader where you can get many different things, and also some non-physical effects if you need them. Got another shader now. One new addition is the new Toon shader that we have. So this one is obviously not a physically plausible shader. It's one that renders very quickly, just with the ray tracing and micropolygon engines. And it's made up of 2 parts here. In here. The Toon color shader and the Toon outline shader. So the color shader takes care of rendering the colors inside the object here, and the outline shader takes care of these outlines. And they're applied to 2 separate objects. So you'd usually need an instance of your object where you apply the outline shader, and then the object itself for the fill color. And one thing I've done here in this scene is I've actually just got this one instance of the shader that's applied to both objects, and the color comes from some geometry attributes that I have on here. And to apply these quite easily, we have this Toon shader attributes sub, where it can set the various colors for for the highlights, the shaded and the shaded areas directly. And just set them for certain primitive groups. So in this case, I've got a separate group just for the eyes, where I can set a different color, so that just overrides the shader attributes here. And then for flip over here, I've just set some different colors. So this is something that's actually probably fairly viable for a lot of models, where you might get away without actually applying any textures and just setting these colors for the various primitive groups that you have. This idea of overriding shader parameters with geometry attributes also applies to all the other shaders, of course, and is very easy in Houdini. Let me show you that with the principled shader again. I'll just try to get a simple chocolate shader. Just set my colors here. So something you might want to do, for example, if you simulate some melting chocolate or something like that, for example, using the new viscous fluid tools in Houdini 15, you might just get an attribute out of the sim for your heat, and it's very easy to tie that to the shader attributes. So, for example, chocolate would usually get a little bit more shiny as it melts. So you might want to vary the roughness here. So this might be your look for your molten chocolate, and then this would be your normal chocolate shader. So to do that in subs, I'll just show that with point wrangle. If I just create the attribute here, that's going to override the shader value. So you could, if you get your heat attribute, you could just rename that to rough, which is the internal name of the shader parameter here. I'll just create a simple example here where that varies in space. So I'll use the relative bbox command in vex. Get the relative bounding box position in Y, and I'll just create a transition here with a fit command, something like this. So within the bounding box, between the values 0.4 and 0.6, somewhere in the middle of the object, this is going to transition between a roughness value of 0.2 and 0.6. So you can see this here. You've got the shiny molten chocolate at the bottom, and then the head sort of transitions to this rougher, dry chocolate look. So these are all things you can do with just the shop shaders, so the shaders that live in the shop context that we ship and that exist in the gallery. If you wanted to go beyond this and beyond the things that these shaders provide, like the texture inputs, things like that. So for example, if you wanted to use procedural patterns with your shaders, you would go into the VOP level. So let's actually go one level deeper now. We can start by looking at how the principled shader is constructed, for example. So if I allow editing on this, which I've done already, so match current definition brings me into this state where I just have the comment here and no nodes, and allow editing of contents actually loads the VOPs that this is made of. I'll just maximize my network editor here so we can get a good look. You'll see a common theme with all these shop shaders is they actually have another shader VOP inside, which encapsulates the core functionality of the shader. So in the case of the principled shader, it's actually very, very similar to the shop version, where you have all the main parameters that are the same, just without any texture inputs built in, because these are separate VOPs here, separate surface color VOPs for each of the major inputs. So even though it may look a little bit intimidating at first, but it's actually a very structured thing where it's just a repetition of the same kind of setup. You can also see the tangents coming in here, which are used for the anisotropy parameters, which I can show as well in a second. And then this is the network that brings in the normal vectors from the surface, which compared to older versions, this sort of network looks a lot simpler now because it uses this displacement texture VOP, which encapsulates a lot of the functionality that was just loose nodes before. So this makes it very easy to use, displacement mapping and normal maps in your own shaders. So this supports all the new modes that I was talking about before as well, like displace along normal and then the new vector displacement, bump mapping, normal mapping, and the normal and vector displacement, normal mapping and vector displacement, they can be applied in these different spaces now. So UV tangent space is supported across the board. And you've also got some new options here to make these more compatible with the various different kinds of normal maps you might get from other packages, where sometimes the X component or the Y, more commonly the Y component, is flipped. And sometimes you just, you don't get the normal map values compressed into the 0, 1 visible range. Sometimes you get them in the original -1 to 1 range, where it's just the normalized vector written straight to the texture. So that's all supported now. And when you use the new baking features in Houdini 15, you can also bake to these various formats as well. I'm going to zoom out and just look at the displacement mapping down here. So this actually looks very similar. It just uses the same displace texture VOP because that supports all these different modes. The difference is that this is outputting to the displacement outputs of the shader, whereas the normal mapping stuff goes right into the shader itself to modify the normals that are used within there. So let's jump to a different scene now and try to use this VOP shader directly, which you might want to use if you need to build some more custom things. So to do that, I've just got a clean scene here, and in the shop context, I'll just create a material shader builder node. And this is what you apply to your object. It's just going to render black by default. And so the material shader builder sort of gives you a clean slate with just the shader outputs for surface shading and displacement shading, and some globals that you can bring in. And if I create the principal shader here, which by the way, you can access all the different shaders through the shader menu in the tab menu here. That'll also create a compute lighting node. So that's actually a big difference to Houdini 14 and older versions, where the lighting computation used to happen inside these types of VOPs, like the surface model VOP. But because we have the ability to layer shaders now, so in that case you might have multiple instances of these that you're mixing. You don't want to do the lighting computation and all the heavy ray tracing that happens in there for every instance of these shaders. So you do your layering and your mixing first, and then you usually have a compute lighting node at the end here that then outputs the various components that the shader expects. So this CF is the actual computed color values, that are computed using the lighting information in your scene and all the ray tracing that has to happen for that. And then you have the opacity, and the F is the BSDF, the bidirectional scattering distribution function that Mantra needs to know how light is scattered on the surface of your shader. By the way, this something you don't really have to worry about too much, but just a detail about this CF output, the final color. This is actually only used with the micropolygon and ray tracing engines on the Mantra ROP. So these engines rely on the shader doing its actual lighting computation. When you are in physically based rendering mode, one of the two, it's actually not used at all. So I can unplug this here. It's not going to make any difference because those engines rely on the BSDF directly. So with the other engines, the compute lighting takes the BSDF and computes all the lighting information internally within the shader. And with the physically based rendering engines, this happens outside the shader, just using the BSDF. But we still have this compute lighting node, and it doesn't actually add any overhead to the physically based rendering mode because it just ignores that part. But it's still useful to extract those components, the opacity and the BSDF from the layer. And it also exports the CE component from the layer, which is used for emissions. So just always, usually you want to have this node at the end of your network. Even if you just work with straight BSDFs and don't use any of the layering stuff, you just plug in the BSDF in here. So let's have a look at how we can use some of the layering features. So here I have the default principal shader. And let's say I want to combine this with another shader. So for example, I could just get another instance of a principal shader, just with some completely different settings. I'll just make that a metallic thing. Add a layer mix. And by default, this is just going to give me a 50-50 blend between the two shaders. But then I can use any sort of procedural pattern or textures. Let's just start off with a texture. Surface color node. And I'll just bring in a black and white checkerboard. So this is going to give me the one shader in some of the areas and the other shaders in shader and others. So one big advantage of this method versus just texturing each of your components, which can give you a similar or the same result. But one advantage of this method is that each of the shaders can be very simple, right? So you don't need to build these huge generalist shaders like the mantra surface, where you have everything in there, everything that you might possibly need. With this, you can just pick the components that you actually need and then combine them in various ways. And it also makes it easier to build. For a lot of things, you can just use fairly generic shaders here that don't have any object-specific textures. Just your tileable scratch maps and things like that. And then, for something like like an object with a paint layer where you have some scratches where metal shows through, you might only need an object-specific texture for the blend map that blends between your color shader and your metal shader. For example, in this, I just have a simple example here to compare between the two methods. So this one uses a shader without any layering. I just have a shader where I've textured the base color as well as the roughness, and I've added some displacement to that as well. This is how you do that, by the way, the set layer component. So that just takes the surface shading layer from the principal shader and adds position and normal for displacement mapping. And let's have a look at the textures here. So these are very standard textures for the base color and the height and roughness. So you can see each of them has this sort of paint area because my height is different for the painted area as well as my roughness. So I have to have that in all the different ones. So that doesn't really allow me to have a generic shaders that I just mix. You might need this for a lot of situations, but sometimes it can just be easier to go the other way, where with this other scene, the layering scene, I have I have my concrete shader up here where I just use a tileable texture from the ones that we ship, just a simple concrete shader that doesn't have any of this painted, this mask in there. And then a paint shader where I just have a basic constant color. And the only specific texture that I have for that is actually this blend mask. So that keeps things very clean and simple. So let's look at some other things you might want to do in VOPs now. So of course you can still texture any of the parameters that you have on here. Like, I'll get rid of the layering just to keep it simple. Just render that. So for example, if you wanted to add some variation just to the roughness on this shader, you could use a texture for that. But then you also have various pattern generation and procedural noise tools here in these menus. I'll just use a unified noise on there and input a rest position into the position input. So that's just going to give me, I don't have any rest attribute on the object, but this is just going to give me a object space position here. And plug this into the roughness. And just to get a quick look at the noise that generates, I'll plug this into the emission input. Just like to do that as a quick visualization. I probably need to increase my frequency quite a bit here. Turn off the auto update. And then on here you also happen to have these output range parameters, which I can use, to map to min and max roughness value here. Refresh this now. And I'll add some fractal noise on there. So if I apply that again, I'll plug in the layer input again, plug this into the roughness. You can see some variations happening there now. Another example, which is actually quite useful for layering as well, is the new dirt mask VOP. That uses some ambient occlusion just to find little crevices in objects. So I'll just use this with the roughness as well, or actually I'll plug that into the emission again, just so we can quickly visualize it here. So if I just render that, you can see that it finds these areas right away, and then you can set your distance. And we actually have this bias direction parameter, which you can use to bias the this mask to in a certain direction, so you get more dirt below, things like that. And then it's actually very easy to plug in noises into this as well. So if I use this unified noise, for example, and use this for my distance, I'll just change the values here so we get some variation around this value. So go between these values and then plug this in. You get some nice variations in there. And then of course you can use any other nodes to edit the mask. So for example, a color correction with a bias. Turn off the auto update again. high bias value just to get a much harder mask there. Maybe a less extreme bias on the dart mask itself. Some smaller values here. So you can dial this in very quickly. And now I can use this, you know, I could just plug this into something like the roughness map here. And plug various versions, like differently color corrected versions. Into the various components of my shader. And of course, like this is a great, also a great thing to use with layering. So if you wanted some, you know, dirt accumulating in these areas, you could just set up a different shader for your dirt. So set up a very simple one. Just a sort of brown, dark shader, high roughness value, and render with that. So now I can use this mask to blend between these two. I'll just use a layer mix again. Plug in the texture or my pattern here, my mask, into the layer mix alpha. And that gives me some dirt in those areas. I have another example of that here. I just have this ship. So this dirt was also rendered with that same method. You can see the dirt mask here. I'll just quickly render that. I'll just unplug the layer here so it renders very quickly. I'll just zoom in on one area. So here you can see the effect of these parameters very clearly as well. This bias causes more dirt to accumulate below these parts here. If I turn that off, or if I set that to 0, you can see that it's a lot more uniform. Turn off the preview. If I increase the value here, you can sort of see the dirt moving lower and lower. And of course you can reverse that by just changing the bias direction, or reversing the bias value. Or if you want, you know, more dirt to be coming from the front, something like that, just set a different direction. And then of course you can vary the direction spatially as well. You can plug in, you know, procedural maps into this as well, or just use a geometry attribute to vary any of these things, anything you want. So in this case, I'm also using a layer mix to mix a metallic paint shader with a simple dirt shader here. And again, each of these is very simple. And in a production setting, you know, you're probably going to texture some of these things. You're going to have variations in color and roughness in there, and in here as well. Maybe the dirt is just a simple tileable, some tileable roughness and base color maps. And then the actual blending could happen in this layer mix again. Let's look at one more example of layer mixing, which you might need in some situations. I'll mix the principled shader just with a glass shader. So that's just another shader that lives down here at the VOP level. Get rid of these. And again, I'll just use a checkerboard texture. Plug the glass shader into the B input and render that. So you can see that some of these areas are transparent now. I'll just set the roughness at 0. So this is something you might need in a few instances because the principal shader doesn't have any transparency built in. So if you need to do something like glass with some dirt on it, or anything else on it, this is how you can do it fairly easily. So these methods already give you a lot of flexibility, and you have the advantage that you still have these fairly high-level nodes here that are easy to use and that you can combine in various ways. But you can also go one level deeper and basically build your own versions of these. The way you would do that is let's have a look at how this is constructed actually. I'll maximize my network editor again. You can see here that the structure of this is actually fairly simple. And what you have here are the various shading components, like the diffuse, the base reflections, and code reflections, which are just added together for the most part. And then you have various things, for controlling reflectivity here, for example, and for getting the normals correct from the input, and various parameters to control the various shading components. And basically the most fundamental element of all of these shaders are the so-called BSDFs, the bidirectional scattering distribution function. The purpose of that is to basically control, define how, for mantra, how light is scattered when it hits a surface. So I'll just create a very basic example again. Start from scratch. So maybe the simplest example is the physically based diffuse, which outputs a BSDF here. I'll just plug that into the surface output directly, which, like I said before, if you're in ray tracing or micropolygon mode, this is not going to work. You need the compute lighting. So it might be best to just always create that and plug in its outputs here, and then plug this into the BSDF input. So when I switch to ray tracing, this is going to work regardless of the rendering engine that I'm using now. So without this, you'll see that, I'll switch on the auto update. You'll see that Mantra basically doesn't know what to do here. It doesn't know what to do with light rays that hit the surface. And this BSDF is what gives it that information. So it's a set of various functions that Mantra uses depending on the rendering engine and depending on how it's, what type of calculation it has to do. But basically, it's a way of telling Mantra, for a ray, for a light ray or a camera ray coming from a certain direction, how is that, how does that ray continue to travel after it's interacted with the surface. So in this instance, this BSDF is basically, it's a diffuse BSDF, which means the light is reflected fairly uniformly in all the various directions, which is how you get this soft light, where you can't really see any sharp details or anything like that. So in contrast with that, something like the physically based specular, that's going to give me a very different look. But the only difference is really how the rays that reflect from the surface are distributed and what their intensities are. So this is all defined by the BSDF. So a lot of the things that are important for the look of your shaders are actually parameters to these BSDFs and control how these things behave. Now the diffuse BSDF doesn't actually have all that many settings, but the specular has quite a few. So let's just get a closer look at this. Probably the most important thing is always the roughness setting. And with something like the GGX BSDF, so this physically based specular VOP encapsulates a few different BSDF models here. And with this newest one, the one that we added in Houdini 14, it's an instance of a so-called microfacet BSDF. And what that means is for every ray that Mantra samples against this BSDF, it uses a slightly different surface normal. So it actually simulates variations in the surface normal at the microscopic level, basically, which these variations cause these blurred highlights because for each surface normal the ray is reflected in a slightly different direction, and the higher your roughness value is, the more or the greater those variations are. So if I set that to 0, all those normals are actually going to coincide with your surface normal, so all the rays are reflected in the same direction. So you get these very sharp highlights here from my area light. And as I go higher, they're just going to be blurred more. And this is also how something like the anisotropy is simulated. I think to show that, I'm actually going to need I need to input some tangent information for the surface here. This by default just uses the intrinsic tangent space of the primitives of the polygons that I have here, which isn't that useful. So usually you want to plug in a compute tangents node here. Just switch that to compute from UV. Plug that in here. Oh. And then that's going to work. So if I render this now, I'll just render a quick one without any anisotropy, and then set it to a fairly high value. So you can see, I did that a bit early, but you can see that the highlights stretch out here, and the direction of that is relative to your UV space. So with the anisotropy direction set to 0, this is going to be aligned with the U direction of your UVs when this is set to compute from UV. And setting that to 0.5 rotates it by 90 degrees, so it's going to be in the V direction. We changed this across all the shaders, by the way, so this is always a 0 to 1 parameter, where 1 is a rotation by 180 degrees now. And the main reason is that it just makes it a lot easier to texture these things. So a texture artist could just easily try a value here to get the right direction visually, and then just take that value without any weird conversion or math on it, and just plug that into Photoshop and paint this texture value into the texture. And then, when you apply that texture, you get the same direction that you were testing here. Let's jump over to this visualization of these BSDFs that I have here. So this just shows you how a ray coming from this light source that hits the surface might travel on after it's due to a GGX BSDF. So this is the same BSDF that we were just looking at, and you can see. So for every ray, it's just going to take one of these directions, and this is all defined by the BSDF. So pin that here. So depending on my values, you'll see this change now. If I go lower in the roughness, you see that more and more the rays are just reflected in a single direction until the extreme case of 0, where they're all perfectly in the same direction, and they're becoming more intense. So the longer the line there, the more intense the light would be there. And if I increase this to 1 to the extreme case, you can see that because it's reflected almost uniformly now, the light direction doesn't actually have that much of an influence anymore. It doesn't make that big a difference, which corresponds with the visual result you get, where it's all fairly uniformly lit and very soft. You can also see the effect of the anisotropy here. So if I increase that, you can see the highlights stretching in a certain direction there, and rotating as I change the anisotropy direction. By the way, the the sum of all the intensities across all the different directions is always going to be constant with a correctly implemented BSDF. So decreasing the roughness here increases the intensity of individual rays, but decreases the intensity of a lot of other rays. So the sum is always the same. So you're basically preserving the energy of the light coming in here. Let's have a look at some of the new features in Houdini 15 with these. So one thing we have now is the Fresnel blending integrated into the BSDF. So the effect of that is just that it computes the actual correct amount of reflected light based on the angle that the light hits the surface. Looking at that here, you can see that a light ray hitting the surface head on hardly produces any reflection. And then as you get to shallower angles, you get more and more reflected light until it's actually fully reflective again. So previously you would always have to do this outside of the BSDF as sort of a post-process. So you would do something like take the Fresnel VOP and multiply this with the reflection intensity that's coming out of here. And at low roughness values, these are actually equivalent. So if I make a copy of this one here with the Fresnel blending turned on, I'll turn off the preview, switch over here, it should be identical. So that's all good, but as you get to higher roughness values, this method here where it's integrated with the BSDF is actually a lot more accurate. Because it's taken in, this Fresnel effect is taken into account at the microfacet level. Which just means, you know, because at this grazing angle you have all these different varied normals. Some of them reflect more brightly and some of them less brightly. And the mix, just the average of this actually produces far less bright highlights, which is much more physically accurate than something like this, where if I set the same roughness value here, you'll actually get fairly bright grazing reflections, which is not always the right thing. So this is why this is integrated with the BSDF now. It also makes it very easy to build certain things, like for example building a simple glass shader. One way to build these now is you just take two physically based specular VOPs and set one of them to refract. So the way this works is when this label matches this list of refraction components on the mantra ROP. So this can be a space separated list of multiple components of anything. This BSDF behaves as a refractive, it's going to refract the rays instead of reflecting them. So this should give me that. I'll just turn down the roughness so it renders more quickly. So this is my refraction component now. And because both of these are Fresnel blended already, I can just add them together and I get an energy conserving result without having to do any Fresnel blending externally. So this is already a sort of correct basic glass shader now. And the nice thing is when I increase the roughness, I get very accurate microfacet reflections for both reflections and refractions now. Let's just have a look back at the visualization here. I can turn on refraction as well now. So this basically visualizes what would happen there now. So you can see the intensities as well as the directions of both reflection and refraction. And we can look at some other effects here as well, like if the light is coming from inside the surface. So for example, the light ray has entered a glass object and is then exiting again. You can see that it behaves quite differently just because the indices of refraction are now inverted. And you can see, you can also see the effect of total internal reflection here, which is something that happens beyond a certain critical angle, where if the light ray is fairly shallow and the material that the light is coming from has the higher index of refraction, all of the light is actually reflected, and none of it is refracted out of the object. And that's actually how things like fiber optics are able to work across large distances. Just all the light bounces around in the fibers, and none of it is able to exit. So this is all handled inside the BSDF now, and it all, should all be modeled correctly. So another way, or another related method there is the reflectance parameter. If you have Fresnel blending on, this actually just acts as a tint value. So you can use this with Fresnel blending and then also apply a tint on top. The other way you can use it is without the Fresnel blending, where it just acts as your reflectance parameter for for the parts of the surface that face the viewer, face the camera. So in this case, you actually have to get a realistic surface. You actually have to take care of the intensity of this value as well. For something like for dielectric materials, these values are actually they usually are very low. So in sort of the 0.04 range, this would be something, like a typical glass material. And of course, for glass, it would usually not be colored. And for metals, you would have a colored value here that's much brighter. So this is actually this exact parameter is actually what's used in the principal shader. So you can build this fairly easily yourself as well and use these in your own materials, in your own shaders. So hopefully this gives you an idea of how to build some shaders out of these BSDFs. But let's look at a few more examples. For example, to build something like a basic plastic material, you'd usually want to combine a diffuse with a physically based specular. So to do something like that, I'll just use the old Fresnel method here. Reset all of this to just 1. And you want to combine these with Fresnel blending as well, so that at angles facing the viewer you get mostly just the diffuse, and at grazing angles you get reflections. So the intensities for reflection and transmission that the Fresnel VOP gives you take care of that. So one simple way of doing that is just with a mix VOP. So you plug each of these into the mix inputs, and then so where the reflection is at its most intense, so where the reflection is 1, we just want the physically based specular result. So I need to plug in the reflection intensity into the bias input here, which, so when this is 1, it's going to use all of input 2, which is the physically based specular. Plug that in here. That's probably a bit bright. Just set that to a medium gray. So this gives me my basic plastic look. And then, so the color for this, like we talked about before, for something like a colored plastic, none of the color would actually be in the specular reflection. It would all be in the diffuse component. So this is where you would set the color now. It should give us a fairly realistic result here. So let's also think about like how this integrates with the new layering stuff that I showed you before. So let's say you wanted to build a custom shader for some parts of your object, and then use that with the standard principled shader for other things through layering. So one simple way you can do that is just take, let's actually look in the shading layers menu here. So there's a few nodes here to work with layers, and you want to use the layer pack for this. So the idea here is that you take your individual shading components and pack those into a layer. And then we plug the layer into the layer input of the compute lighting. So this is basically the same setup that the principled shader and other shaders that we ship use. So in this case, we should just get the same result. And now you could also decide to wrap this up into an HDA, that you can use across your production. I just hit Shift C there, or use this icon to wrap that up into subnet. And then you can promote some of these parameters, and then you basically have a shader like the ones we ship. So you have all the freedom here to combine BSDFs in various ways, which is usually all that happens with these physically based shaders these days. It's just combining various BSDFs, and if you need even more customization, we also have the ability to create your own BSDFs using the Vex language. So for that, there's some documentation on that, on how you would do that. So this is where it gets fairly technical, but all the that ability is there as well. So this is something you would do when maybe a new BSDF comes out in a SIGGRAPH paper, and this is how you could implement those things. But for 99% of the cases, you should be okay with one of the BSDFs that we ship and just combining them in various ways. So just to show that as well, let's jump up a level and then just combine that with the standard principled shader. So again, you can now just layer mix. So just another variation of that. So let's just let's look at a slightly different example here. Let's look at volume shading for a second. So this is a simple volumetric cloud that I've simulated with the Pyro tools. And in the scene, I just have a area light, rectangular area light behind this cloud. And I just want to show you how BSDFs come into play here. So it's basically all the same concept. So the BSDF is also responsible here for defining the direction in which light travels after it interacts with, well, not a surface in this case, but just with the volumetric matter. So the one important component here that controls the BSDF on the Pyro shader is the scattering phase. So all that controls really is the direction that light is scattered when it hits the particles or the imaginary particles in that volume. So as I increase that, light is scattered more in the direction of the original light ray. So you can start to see the shape of my light in there, just because at these other angles we're not getting that much light scattered into those. And if I go to fairly high values, you can see the shape very clearly here. And if I actually go to negative values, you'll just see it get darker because all of the light is scattered backwards. So if I were to rotate my camera around to the other side, you'd see very, very bright smoke there now. And by the way, the Pyro shader has received some attention in this release as well. We've actually made it's basically written from scratch, but has most of the functionality still in there, just in a much more condensed and clean interface. So we've tried to put all the important parameters on basically a single tab, so you can tweak things, the typical things that you have to tweak and balance against each other, like the smoke brightness, density, the fire intensity, and the way it maps to color, where the black body mapping was fixed as well. That always produced just orange results before, and we found a problem there. That's all on one page. And then the things that you also had before, like the all the remapping things for the various volume fields, those are all on their own tabs and are still all there, just identical tabs for each one of the fields. So yeah, that's the new Pyro shader. So hopefully this gives you a good idea of all the various ways you can do shading in Houdini 15. So just to sort of give an overview and summarize again, you have the shop level where, let's just look back at this scene principal shader here. So you have the shop level where you have these sort of full featured shaders with, complete with texture inputs and UDIM support and everything, although that's also supported at the lower level just the same. But everything sort of integrated, which try to give you, what you might need for most cases. So this might be the first thing you try and see if it gives you everything you need for whatever you need to shade, and then you can go, progressively go deeper and customize things more as you need it. The great thing is, since this is Houdini, you can jump into all these things, just like you can do with something like the DOP dynamic solvers. Just jump in and modify these things, and then even make new HDAs from just the slightly modified versions of these HDAs, and publish those and use those across your production, across your projects. And then you can go one level deeper and just use the layering and use these, use the VOP version of each of the shaders, combine those in various ways. And if that still isn't enough, you can go one level deeper and just build those things out of, again, just jump in there, use these as examples of how to build shaders, and just construct your own shaders from the fundamental BSDFs that we ship. And of course, you can also write your own BSDFs just in the Vex language. So you can go another level deeper there. So hopefully this shows that we have this whole gradient of functionality where we have these fairly easy to use shaders that are easy to use out of the box. And you can go as deep as you want. Right. I think this concludes our masterclass on Houdini 15 shading, and thank you for listening, and until the next time.